Hi everyone, thanks a lot for coming to my talk. Before I begin, I'd like to thank everybody at Krell and DOE for making the SSGF such a wonderful program. It's been a huge blessing to me. I've really enjoyed it, met a lot of friends and mentors through it, so thank you very much. Today I'll be talking about water and water at ambient conditions, but primarily at extreme conditions. And I'd like to start first with an outline, so I will be motivating why we are interested in this at all. I'll be talking about how we model water on computers, and then I will tell 4 vignettes from my own research. So why are we interested in water at all? Well, you really can't overstate how important water is. It's necessary to life, geochemistry, planetary science, industry, and it has very deep significance amidst cultures. We have to remember that water is not just that famous molecule that we think of, it is actually a system of molecules. In fact, it is the quintessentially hydrogen bonded system. And that hydrogen bonded nature is to credit for many of the very unique and anomalous properties of water, some of which I listed here. My research is focused on what happens to these properties and really the nature of water as you perturb it, whether that is through solvation of ions, some kind of confining media, or through the application of high pressure and temperature. So there's many different ways to think about studying water. I've chosen to study it using computational modeling. And the history of computational modeling is actually linked very closely to the history of the study of water. Water has always been one of those test systems that people use, from some of the earliest machines to the newest leadership class, which will be coming to Livermore in 2023, El Capitan. There's many different models to study water, various levels of approximation to make. And here in my studies, I've been using the quantum mechanical, which is the most expensive, but in many ways the most precise. And I will be specifically using the tools of density functional theory, which is, at least in principle, it is a formally exact description of the ground state of any many-body quantum system. Now, we use DFT as an engine. I like to think of it as like the engine, the driver of molecular dynamics, so the time propagation of a system, by taking the energies and getting forces from them. So from these forces, which are derived from first principles, we can then propagate a trajectory, and then we can talk about that trajectory itself being a first principles trajectory. Furthermore, along the way, as we compute the trajectory, we can compute things using first principles theory that we might not be able to do in other ways. And I'll talk about that more. And I'll here say that we're using the Q-box code to do first principles MD. So the first vignette will be about statistically robust studies of monovalent ions in bulk water. So you might think, wait a second, isn't that just salty water? And don't we know that pretty well already? Well, it turns out this has been studied for a long time, but there are still many mysteries and a lot of controversy, both in experiment and in computation. One of the biggest ones is about the extent of the effect of ions on the structure and properties of water. Most importantly, the global effect, in other words, not the local, so not really close to an ion, which we call the solvation shell, but far away from it. Is there a long-ranging effect? So that's kind of what we tried to attack primarily. And what we brought to the table, and this was done during my practicum at Livermore, was to look at statistically robust simulations. What that means is that we actually launched 10 different systems for lithium, sodium, and potassium, each of which was its own trajectory. And in so doing, we could actually get statistical averages of certain quantities that, at least in first principles MD world, are not often reported with statistical precision in the way that we can if we have independent trajectories. One of those things would be a quantity like we show here, which is the hydrogen bonds per water. And the dotted lines here are the reference for pure bulk water, I should say. We then can compare our first solvation shell water, which is here. They're all below. In other words, they have fewer hydrogen bonds. Second shell, which here we see in the inset, is actually all enhanced relative to bulk water. And then really that crucial thing, which I call bulk here, what that means is everything beyond the second solvation shell. So this would be if there is a global characteristic or a far-ranging characteristic that one of these ions, at this level of theory at least, breaks or makes hydrogen bonds, it would show up here. And with our statistical analysis, we found that it does not. So these ions, at least with this model, are not structure makers or breakers. We found a similar message about diffusion. So here we have many different diffusion curves. So these are mean square displacement curves. You can see really what the range is across a statistical sampling of many trajectories. Each line here corresponds to an independent trajectory. And when we analyzed these as well, we found similarly that we couldn't find meaningful differences among the ions. So what can we turn to? Where could we find and discriminate between these ions? So we, with some reason, turn to a quantity which is the molecular polarizability. And I won't dive too much into the technical details here, but I will say that this is the extent to which a molecular charge density changes due to an applied electric field. And this has been done often with dipole approximations, where there's only dipole-dipole interactions that kind of go into this. And the method we used comes from using the inverse dielectric matrix developed somewhat recently, and this is accurate to all multipoles. So when we examine this, we find that there's actually quite a difference between the ion solvation shells, which are shown in red, and the non-solvation shells, or the total water, which is shown in the dark upstairs. I should say up here above the ion solvation shells. Furthermore, we were able to find that it's actually what is shown in Z here, the out-of-plane, perpendicular out-of-plane part of that tensor that is the most sensitive and has the most statistically significant differences. So what we're able to do then is verify and generalize a conclusion about what molecular polarizability can and cannot say, and found that it's a really sensitive fingerprint to even discriminate between these ions for ambient water. So I'll just conclude here this section by saying we found that we couldn't find structure-making, structure-breaking effects from structural analysis, I should say, or diffusion, but we were able to find far-ranging effects in the molecular polarizability. And we also did use this data on potassium in a different study that had to do with isotopic fractionation, but I will not get into that here. So we use this ambient data then as kind of a platform, a basis for comparison for looking at confined aqueous solutions. So why do we compare about confinement? Well, this is both fundamentally interesting, but it also has a lot of applications, whether for little biocapillaries in our bodies or for desalination technology, where people are looking at carbon nanotube membranes. There are many anomalies, very strange behavior under confinement, and we here chose two confinement diameters. Here you can see a top view of a 1.1 nanometer diameter carbon nanotube and a 1.5. These are two important diameters for several anomalous things that happen at these radii and radially dependent properties of water. So we're able to first verify certain things about structure of these salty water solutions inside the carbon nanotubes. And then we also looked at comparisons of the dipole moment under confinement versus in the bulk. Now, this type of thing has been studied before, so this was primarily a confirmation that the dipole moments are reduced under confinement. On the other hand, the molecular polarizabilities, here the bulk on the left and the confined on the right, are enhanced. And as we dove into this, we found that this enhancement is radially dependent. So here I'm showing the binned radius relative to the, so like going outside from the inside of a nanotube. And we found that the dipole moments are reduced more and more as you go closer to the interface. And the molecular polarizabilities are actually ramping up. So the extent to which it is enhanced seems to be coming from the those parts of the water that are closer to the interface. So the nice thing about computational studies is that we can really do something like just removing the carbon and computing the same properties. So that's what we do here, where we look with carbon nanotubes, in other words, literally with the charge density that comes from the carbon and without in the dipole moment. And if you compare this and you say, well, that looks pretty similar, that's because it is. The dipole moment doesn't change much with the presence of the carbon nanotube. However, the molecular polarizability changes a lot. So this was, if you remember, it was enhanced even relative to bulk, but it is actually decreased even below bulk when you don't have the carbon nanotube there. So when you kind of unravel and put this together, what we found is that there's a competing effect between the breaking of hydrogen bonds that happens at the interface, close to the interface in the water, and also kind of a fundamental increase that happens due to the interaction with the interface. And this leads to a moderate enhancement overall. Overall, what this was showing is that it is the molecular polarizability, again, that is this very sensitive fingerprint and can really discriminate between different types of chemical effects that are happening in these systems. This work was featured by GCP, AIP, as well as Livermore News. And again, these two sections were all done in collaboration with my practicum advisor, Anfam, and Eric Schweigler, who are at Livermore. Now we'll turn to talking about high pressure and temperature. And the first part of that will be looking at pure water and focusing on spectroscopy, as well as the ionic conductivity. So the phase diagram of water is very complex. Some might say it's a mess. There are many different crystalline phases, a lot of different things going on with superionicity. We are interested here primarily, here I'm showing a simplified phase diagram in still high pressure, but kind of a lower high pressure than some of those really crazy things that happen in a lot of these advances, especially experimentally recently. So we're looking at 10 and 20 GPa. I'm marking here are the places where we have MD trajectories with the yellow stars. And then also we look at a trajectory down. This is actually not I7, this is a quenched phase. So it's kind of an amorphous phase, which I don't have time to talk about much. This is important for planetary science. This is important for the properties of the upper mantle of Earth, which is around these pressure temperature conditions. And there's a lot of controversial results. So we're trying to just basically understand what is going on here from a first principles point of view. We're able to establish a lot of dissociation. This is an RDF, radial distribution function, which establishes, especially in this region, that there's a lot of molecular dissociation. And furthermore, we can look at the type of dissociation going on. And it's not all just hydroxides and hydroniums forming, though those do form in correlated fashion, which I'm showing down here. There's a veritable zoo of ionic species that form in the dissociation processes. Some are what they call Zundel-like, some are Eigen-like, and there are much more complicated species that emerge for really short lifetimes in the dissociating water. And so we've kind of seen that there are these strange species that are emerging, all very short lifetimes. And we want to understand, is there any dynamic effect to these? Primarily, what is the effect on the electrical, namely ionic conductivity in this realm? Here we are using a Green-Kubo relation, which as far as we know hadn't been attempted fully from first principles using maximally localized Wannier function centers. We have a Green-Kubo integral, which is coming from the time correlation of the derivative of the sample dipole moment, kind of a mouthful, which can then be re-expressed through an Einstein relation, which looks a whole lot like a diffusion coefficient. It's just that the slope here is not the diffusion coefficient, it is sigma, which is the ionic conductivity. So this was the first we could compute this from first principles, and we found that at 20 GPa, it's about 10 times higher than at 11 GPa. And both of these are 6 and 7 respectively, orders of magnitude higher than the conductivities we have just in the water that we're used to around us, ambient conditions. This was consistent with the experiments that we have seen here. So I'd like to highlight, it's not that the high conductivity was a novelty of our study, but being able to express this and compute this from first principles while also seeing the dissociation mechanisms was what we contributed here. And then we also went further in search of vibrational spectroscopic signatures of these species. So any spectra ultimately mathematically is coming from a autocorrelation function, which is Fourier transformed into some kind of a power spectrum, which then has modes that correspond to molecular motion. And without getting too deep into the theory here, the infrared spectrum comes from the Fourier transform of the autocorrelation of the dipole moment, and the Raman spectrum comes from the Fourier transform of the autocorrelations of the polarizability. And we're able to compute these along the trajectory from first principles. We kind of developed several things, several principles. We found that the vibrational density of states is not sufficient to capture what's going on in the Raman. And we're able to compare directly to experiment here. Our theoretical peak is shown in dark, in black rather, with some of the experimental ones in red and blue. And we're able to say certain things, kind of we took a deeper dive into the inter and intramolecular contributions, and we're able to help in the spectroscopy of that from first principles. However, ultimately, it wasn't in the Raman that we found a signature of the dissociation. We didn't see any new modes or anything like that form. Where we did find a signature was in the infrared spectrum, where there was a lifting of the background continuum intensity with dissociation. So at the higher dissociating 20 GPa case, we saw this broad increase in the background. And this is actually analogous and physically analogous as well to some studies that have been shown in ambient conditions when you have like a really strong, maybe acid solution that's causing an excess proton in water. So there's really an interesting analog between extreme high pressure temperature and these ambient condition excess hydrogen type scenarios. So to conclude here, we were able to study structural things. I didn't get to dive into it, but we were able to say some more things about the I7 melting line. we were able to establish from first principles some of these ionic conductivities, high conductivity with the dissociation, and also we're able to dive into the Raman and the infrared spectra. Now, in the small time I've left, then I'd like to just talk about the last section. I'll just mention this was also featured in New Chicago News and some other places as well. So then the final piece of this puzzle would be then combining ions with the same high pressure temperature water. And for simplicity's case, we didn't focus at all of the same PT conditions we had looked at. We just chose 11 GPa, 1000 Kelvin. Any realistic geochemical system is going to have a lot more than just pure water. You're going to have all sorts of ions, carbonates, all kinds of things mixed in there. And so we were just initially starting with understanding simple ions, namely, again, lithium, potassium, chloride, that type of thing, in this water at these conditions. So one of the interesting things is that lithium actually forms a very long-lived complex where it is flanked by water or oxygen, which has varying amount of hydrogen on both sides. In contrast, larger ions like potassium and chloride, despite the difference in their sign, have very static, slow-moving solvation shells, which exchange with the water surrounding. So the water that's in there actually changes, but they're not nearly as fluid as the lithium solvation shell at these conditions. Global oxygen-oxygen correlation pair distribution functions are not largely changed. In other words, the structure is not changed of water because of the ions at these conditions. 1A function centers are also not significantly changed. Where you do see changes are in the ion solvation shells. So the lithium is reduced, and the potassium is also slightly reduced, and the chloride is also slightly reduced. In contrast, the coordination numbers we see consistent with that flanking, lithium moves from 4 to 2 coordinated, and these larger ions have large increases in the coordination. So there's big changes in the local solvation shells. However, we found that the Raman and the infrared were not very different. In fact, we found the same continuum intensity I was just talking about, but they were not changed because of the ions, similarly with the Raman. We even checked the molecular polarizability, which was that very sensitive fingerprint. And while we did find this is the bulk and the high pressure on the right in the blue, we found some reductions, which is consistent with some other works. They're not very large. So the extent to which we did find signatures of the ions in these conditions, we found it in the polarizability. But overall, the message was one of resilience. So finally, then we looked at the dielectric constant, and this is very important for geochemical models. This comes from the expression here. This goes into the modeling of many rock mineral interactions with water. And we're able to look and find this quantity to be always limited. So the pure water is always an upper limit of this quantity. And the extent to which they're reduced is really quite small, 5 or 10% reductions, but this could potentially help to calibrate some of these deep water models that are used to understand mantle geochemistry. And then finally, last piece is the ionic conductivity, which again we compute, and we did find some significant increases, factor of 3 or 4 relative to pure water in these ion solutions, but we couldn't discriminate between the ionic solutions whether there was a significant difference in the conductivity. So to summarize this, we found large changes in the solvation shells, like that long-lived lithium-flanked scenario, and the very large solvation shells, big increase in coordination. But we didn't see any significant spectroscopic changes relative to the high pressure pure water. And then we're able to make some comments about how conductivities and dielectric constants are changed relative because of the ions. So then just some very general conclusions. First principles theory is needed for things like molecular polarizability, for things like dipole moments. It's very important at extreme conditions. We found infrared to have a lot of efficacy in understanding water at these conditions. And really, I mean, across the confinement, the ions, the high pressure, we found a remarkable resilience of water in many different measurables, I should say computables. And really, that's one of my take-home messages, is really the resilience of water, liquid water, I should say, to many of these different effects. So I'll wrap it up here. Thank you for your patience. Thank you for your time. This is my group in Chicago. These are my mentors, Ding An from Livermore, who is my practicum advisor, Federico Ghiberti, and my advisor, Giulia Galli, of course, I would like to thank. And then once again, thank you to SSGF. Thank you to all of you for listening. And thanks for a wonderful 4 years in the program. Thanks a lot.